How are we today, guys? My name is Lucas, and today we have a small fluids project we're going to run. We got a piece of 3/4 PVC pipe and a 90-degree fitting, and we want to find the pressure drop across this fitting. And then with the pressure drop across it, what is the coefficient of minor loss across that fitting also. So I'm going to do a little build video of what it looks like. I'll explain what's going on, and we'll see what it does. Alright guys, this is my finished product. I decided to use my spigot where you normally connect the water hose. I'm using a hot and cold side hose that would go to your washing machine, just because these fittings are easier to get that way. And you can see what I've done here. I've put a couple of 1/8 inch to 1/8 inch NTP pipe thread to 3/8 hose, and you can see right there there's a slight difference in pressure before and after the fitting. So I'm having fluctuation issues because of course I'm connected to the tap, so anybody else on the, throughout my house or anybody else's house that turns on a valve, there's a pressure drop. So right now it's slowly building as if no one's using it. But I digress. So what I need to do now is take this hose and time how long it takes to fill that 5-gallon bucket and measure the difference in pressure on those two hoses, or the difference in head, really. So I'll be back in my room to show you the math on this. Alright guys, we made it inside. While we were out there, we measured the flow rate of our little system out there. we saw how long it took, or I measured how long it took to fill up a 5-gallon bucket, and it took 3 minutes and 6 seconds. And we need that along with the head loss across that fitting, which was 1 centimeter, to find this KL. This is the minor loss across that fitting, the coefficient of minor loss across that fitting. And if you look at this Q equals AV, that's the flow rate is equal to the cross-sectional area times the velocity. The flow rate, Q, we can find from this 5 gallons in 33 minutes and 6 seconds. So 5 gallons in meters cubed is 0.0189. And we take and divide that by 186 seconds, 3 minutes and 6 seconds, to find a flow rate of 0.000100175 meters cubed per second. So we plug that into this Q equals AV, 0.000100175 is equal to pi over 4, and then the diameter was 3/4 of an inch, which is 0.01905 meters, because you got to be consistent with the units. So 0.01905 squared times V. V is 0.35702 meters per second. And now we can plug that into this head loss equation. So 0.01 meters is equal to the head loss times the velocity squared, 0.35702 squared, over 2 times 9.81. And we find that KL is equal to 1.539. So what were we looking for? We were looking for a regular 90-degree flanged fitting, which would be 0.3 for KL. I am assuming that the difference has to be because we're not using a constant flow rate, not a perfectly constant flow rate, because I was attached to basically city water, and anytime someone opens or closes a valve in anybody's house, there's going to be a pressure drop and a pressure change when, once they turn it back off, and that way we're not getting perfectly constant flow, causing instabilities in how I'm measuring and or just because the flow rate's fluctuating. But if you were to do this with a constant pump, you should see something closer to 0.3. And you could do this with other fittings if you needed to also, if you wanted to do longer experiments. So hopefully you guys learned something from me, and if you have any questions for me, you'll leave them in a comment for me, and thank you guys for watching.